Many of you already know me, but if you do not know me, I'm Partha Mukherjee from School of Mechanical Engineering at Purdue University, and I started as the faculty advisor to this chapter. And also, I'm really engaged into this ECS scientific community as such outside this chapter for my research and everything. So with that, it's my great pleasure and honor to welcome our speaker today, Professor Veronica Augustyn from North Carolina State University. I would like to just briefly say 2 words about her. Her work is just awesome. And that straddles between the very fundamental deep science and also, you can see that application domain of things. And then with that, she is also a great collaborator and a friend who I know for quite some time over the last few years. So with that, let me hand it over to Sushmita, who is the chapter president, to formally welcome and introduce our speaker. Thank you, Veronica.
Thank you so much.
Thank you, Professor Mukherjee, for the introduction. And welcome everyone to today's webinar organized by the ECS Purdue University Student Chapter. So as Professor Mukherjee mentioned, he's our lead faculty advisor of the Student Chapter. And those of you who don't know us, we have Professor Laskin also working as a co-advisor for this chapter. And my name is Sushmita, and I am the president of this student chapter. So this is the current executive board for this chapter. So as a part of our activities, we have started a webinar series in the last fall with speakers from academia, national labs, and industries. So we are continuing with our webinar series in the spring 2021. And the theme of our series is Women in Electrochemical Sciences and Engineering. So far we had a few speakers from different national labs and industries as well as academias. So just a little announcement that we have Dr. Rana Muthadi from Toyota Research Institute of North America as our next speaker in this webinar series. Now it's my great pleasure to introduce our today's speaker, Dr. Veronica Augustyn from North Carolina State University. Dr. Augustine is an assistant professor of material science and engineering and a university faculty scholar at North Carolina State University. From 2013 to 2015, she was a postdoctoral fellow at the University of Texas at Austin. She received her PhD from the University of California, Los Angeles, and her BS at the University of Arizona, both in material science and engineering. Her research group focuses on the design and synthesis and characterization of materials for electrochemical energy technologies, including batteries, electrochemical capacitors, electrolyzers, and fuel cells. In particular, she is interested in the relationships between material structure, composition, and morphology, and the resulting electrochemical mechanism. She also leads an award-winning international project at North Carolina State, SciBridge, which develops renewable energy research and education collaborations between universities in Africa and the US. Her research group has been recognized with a 2019 Sloan Fellowship in Chemistry, a 2019 DOE Early Career Award, and a 2017 NSF Career Award, among other honors. The talk of her title is Electrochemical Capacitance under Confinement, Implications for Electrochemical Energy Storage and Conversion. Now, without further ado, I'll turn the time over to Dr. Augustyn.
Okay, thank you so much, Sushmita, for the invitation and the opportunity to speak. I was looking at your list of the invited speakers for this semester, and there are many friends on that list for me. So that's great to see, and it's also a pleasure to speak to Purdue University because, as Partha mentioned, we are friends and collaborators, and that touches upon something that I'll talk about at the end of my talk, which is just, I think, one of the really wonderful things about science are these collaborations and these friendships that are formed, especially in electrochemical sciences, where we can go from the very fundamental, which is kind of what I will be talking about today, to the more applied scale. And we can all work together, so that makes it really fun. Okay, so first I just want to mention that I'm a material scientist. So really we are supposed to study condensed matter. But in the course of my independent career, I've become really fascinated by fluids, particularly fluids under confinement and solvation science. So it's kind of an interesting thing that I like to think about from time to time, just how did I get to studying this particular topic, but I just find it very fascinating. So let me introduce you virtually to my research group, at least the way we looked back in 2019. The work that I'll share with you today is predominantly the PhD work of Shelby Boyd, who graduated back in July, as well as graduate students Said and Mike Spencer. We are very lucky to collaborate with a number of computational groups. On this particular work, we've worked with Audrey Van Duyn and Dian Zhang's group for some of the simulation work that I'll show you later on. And the work I'll show you today is primarily funded through the Department of Energy in the Fluid Interface Reaction Structures and Transport Energy Frontier Research Center. We are also very avid users of the DOE user facilities, which I think are just fantastic resources that we have available to do science. Okay, and let me also give you a virtual introduction to North Carolina State University, because I know we have an audience, I think from all around the world with these virtual seminars. So we are roughly where this red star is in the state of North Carolina, so on the east coast of the United States. And we are part of a region that's called the Research Triangle with Duke and University of North Carolina at Chapel Hill. NC State, and this is a picture of our Centennial campus, and this is the city of Raleigh where we're based in. We have about a fairly large student population, over 30,000 students, and engineering is the largest. So Duke and UNC Chapel Hill, well, let me say that Duke has an engineering college. UNC Chapel Hill does not have an engineering college. We are both state universities, and that's one of the distinctions between these two state universities that are in close proximity. Where we are based, the College of Engineering is predominantly on what's pictured here, which is called the Centennial campus. This is a fairly newer campus of the university that's home to engineering, as well as companies and government agencies. So we actually have like the National Weather Service for Raleigh based here, as well as a lot of agriculture, government entities, and so on. So it's kind of cool to have this mixed use campus. And then just in terms of the geography, we're located between the Blue Ridge Mountains to the west and the Atlantic Ocean to the east. So it's a very lovely area to visit if you haven't had a chance to come. Okay, and now going down in scale to our research group, we are a material science group. We make our own materials. A lot of what we do involves soft chemistry routes to functionalizing materials, which I'll show you today. And then, of course, we have to assemble those materials into electrode architectures. And this is actually where we collaborate with Professor Mukherjee's group into making electrode architectures that have optimized ion and electron pathways when you have high mass loading. And underpinning all of our work is the desire to understand electrochemical mechanisms. So what is going on in these materials, ideally at different length scales, starting from the atomic scale. So we use tools like operando X-ray diffraction or operando atomic force microscopy to make that connection between the global electrochemical response of our electrodes and the detailed mechanisms that are taking place. So I wanted to give you a little bit of an overview of how I got interested in this particular research space. There's a series of papers from the group of Dominic Marks on chemistry under confinement, or chemistry occurring in very, very tight spaces. And what's illustrated here is the top and bottom surfaces are a layered material, an iron sulfide layered material that is separated by some interlayer spacing, where that interlayer spacing allows for water as well as organic molecules to be present. And these three different panels are representing a chemical reaction that's occurring in this essentially nano-confined environment formed between the layers of the material. And this particular panel shows this organic reaction here. And here they show the free energy change as a function of the reaction progress if you consider the situation under nano confinement at high temperatures versus if the same reaction was occurring in bulk water at high temperatures in blue or at ambient temperatures in black. As you can see very clearly is that under confinement, that free energy change, that energy penalty is essentially minimized, making these reactions happen much more easily. And I thought this was really fascinating because essentially the material here, the iron sulfide, was providing this confinement template and driving or making this reaction much more favorable. And later on in this paper, I believe they even say that reactions like this could be how some of the early complex organic molecules were made, in the beginning of time, if you will. From an electrochemical standpoint, the similar benefits could be realized. And this is an example from the group of Alex Vojvodic at Penn, where they simulated what's going on if you take 2 sheets of ruthenium oxide and studied the oxygen evolution reaction occurring under confinement, so water molecule going to form oxygen gas as a function of the interlayer spacing between these 2 sheets. And what they find is that the absorption energies of the intermediates, and those intermediates are oxygen, singlet oxygen, hydroxide, and oxyhydroxide, that in the case of the oxyhydroxide, you actually have this very strong dependence on the interlayer spacing, whereas the other intermediates did not. And this would still give you an opportunity to tune the overpotential or decrease the overpotential of the ruthenium oxide because you were able to decouple the hydroxide and oxyhydroxide and the oxide binding strengths from each other due to this dependence on the interlayer spacing. So in a way to basically overcome what are called scaling relationships. So far I've showed you these are computational studies, and in the realm of understanding confinement effects, I think the computation predictions are far ahead of what we've been able to show experimentally with materials. And for an experimental scientist, this presents a really great opportunity. So another thing I want to mention is that one of the fundamental things that will occur under any electrochemical interface is the formation of the double layer or an electrochemical capacitance. And how this occurs under confinement has been the topic of a lot of discussion in the literature. So for example, how does the double layer form on a high surface area carbon? This is a classic paper from Yuri Gogotsi and Patrice Simon showing this increase in the capacitance when the cation size approaches the pore size of the activated carbon, as you have this squeezing of the double layer. On the other hand, if you come to this picture from the intercalation chemistry standpoint, this no longer looks as like a electrostatic response, but rather looks like an intercalation reaction. And that's this idea of pseudo capacitance that has been used to describe the particular response of bernocite manganese oxide in aqueous electrolytes. And I'll talk a lot about this in my presentation today. So besides the fundamental understanding that we glean from knowing how electrolytes organize themselves under confinement, there are potential benefits for high power energy storage. So we think that these materials that contain confined fluids are really a way for us to bring together the benefits of bulk micron scale materials with the benefits of the fast kinetics of high surface area exfoliated materials. And this is detailed in a perspective that Yuri Gogotsi and I co-authored a few years ago. Okay, so how did we get started in this work? It was actually a very interesting pathway. Shelby started her PhD where we wanted to look at layered metal oxides for low-cost aqueous sodium-ion batteries. And then because these materials would essentially be uptaking sodium ions from the electrolyte, that also would make them of interest for electrochemical desalination. And one thing to keep in mind is in the case of non-aqueous electrolytes, we oftentimes can think of this electrode-electrolyte interface as being rather sharp. So the interior of your layered material is not going to be really interacting with whatever's going on in the bulk of the electrolyte because desolvation energy barriers are relatively low, or you have the formation of solid electrolyte interfaces, solid electrolyte degradation products that essentially cause your cation to be completely desolvated by the time it intercalates into your material. And that's certainly the case. That's our operating picture for lithium-ion battery electrodes. But in aqueous electrolytes, you no longer have that that possibility. So you don't have any solid electrolyte decomposition products. They're gaseous, right? Oxygen evolution, hydrogen evolution. And there's a very strong likelihood that your material can become hydrated because of the presence of water. So you have this very, very intimate mixing between your material and the aqueous electrolyte. And we set out to understand what goes on when we place a typical non-aqueous sodium ion electrode material, this class of P2 layered oxides, into an aqueous environment. And so the structure of these materials, these are all layered materials synthesized at high temperatures, about 900 degrees Celsius. They contain layers of transition metals. Predominantly, those layers consist of manganese, separated by layers of sodium cations that are in a prismatic coordination. The P2 just stands for the prismatic site, and the 2 is the stacking sequence of the oxygens in the layers. It turns out that depending on what the dopant is, what the other transition metals are around manganese, to a large degree determines how stable the material will be when exposed to ambient air that contains humidity or an aqueous electrolyte. And we noticed that if we had, for example, iron in the structure, the material was very readily becoming hydrated upon exposure to water. So you can see that in the increase in the interlayer spacing. On the other hand, if the layers contained copper, then their ambient stability was much improved, and before and after water exposure, we could still image these beautiful layers of the transition metals. What happened when we then started to do some electrochemical cycling? So we placed these into a sodium sulfate aqueous electrolyte. If we took those same copper materials, our cyclic voltammograms in terms of capacity weren't perfectly reversible, but in terms of the redox peaks, you could see they were very clear and they were reversible on multiple cycles. So the dashed line is the first cycle and the solid orange line is the second cycle. The gray here is indicative of the acetylene black, which is present as a conductive additive. However, if we had something like the iron containing material, there was a significant difference between first and second cycles. The CV peaks that are present here and here, they essentially disappear. And what we are left with is a cyclic voltammetry response that is very much potentially independent. And that's essentially a capacitive response. So we had this transition from potential dependence to independence, depending on the transition metal layer composition. What was the mechanism taking place? What we found using operando X-ray diffraction is that these materials undergo essentially a first order phase transition to a hydrated structure when some critical amount of sodium is removed. So here's a cyclic voltammogram again, showing this big distinction between first and second cycles, potential dependent, then more potential independent. What we see from the operando X-ray diffraction is that sodium is removed from the structure. We see this P2 phase maintained until you get to a critical amount of sodium deinsertion, and you have this phase transition that occurs very suddenly. Water comes in to basically offset the loss of sodium ions. When we think it's driven by the need to offset the repulsion between oxygens within the layer. This happens very quickly, very discreetly. There's no continuation of this process. And then you're left with this hydrated phase that is still electrochemically active, but in a much more continuous manner, in the sense that this interlayer spacing changes more like a solid solution type process. What happens at the electrode particle scale is that this phase transition is about a 25% C-axis change, and we actually see microscopic exfoliation that leads to failure of the electrode because these particles become electronically disconnected from the electrode. So we now understood the mechanism, and this is what it looked like. So you take these P2 oxides, and depending on the transition metal layer composition, when you applied a critical voltage to remove sodium from the interlayer, water would come in to take the place of the sodium ions. That leads to a phase transition and electrode failure. So that was kind of disappointing, and it was challenging to have reviewers actually publish this study because it wasn't going to give you a record-breaking performance. It was detailing a degradation mechanism essentially. But it made us think that if we are forming this burnasite-like material, and bernocite is used as an electrode material for electrochemical capacitors. And the XRD was showing that this phase was electrochemically active. Whatever particles were remaining adhered to the electrode was responding electrochemically to sodium insertion, made us think, can we harness this process? Can we use this to form bulk-like materials with capacitive behavior? So this is, again, the particles. You can see they're several microns in dimensions. We took the powders and placed them into a dialysis tubing that was basically permeable to our aqueous electrolyte. And then we stuck in here a platinum coiled wire to try to connect as many of these particles electronically as we could, and then applied a really high oxidizing potential to drive sodium out of the structure. And what we got were these expanded and hydrated materials that still retained their overall bulk morphology, like perfectly stacked nanosheets, if you will. Here's another version of these particles. You can see they're like little, I think someone said at a previous seminar I gave, they look like pastry, like flaky pastry crusts. And it does, it's very, very cool. And this is kind of what's going on within the layers themselves. Okay. So the cool thing is that when we take those materials and assemble them into an electrode, a slurry electrode, now we see that the capacitive response is there, and it's very, very reversible. They can cycle for thousands of cycles, and their capacitance is actually very similar to the commercial activated carbon used for electrochemical capacitors, which is surprising because we start with a material that is orders of magnitude lower surface area than activated carbon. Remember, we start with a material that's 900 degrees Celsius synthesis of an oxide, and now we're getting capacitive response that's like that of activated carbon. So that's pretty cool from an application standpoint, and we think these kinds of top-down electrochemical tuning of materials could be interesting for other applications, but it did make us think about the nature of the electrochemical capacitance that's occurring in these particular materials, where we know we actually don't have a very tremendously high surface area, or outer surface, I should say. And so it led us to this thinking about electrochemical capacitance under confinement. We know fairly well what's happened to the organization of ions at a planar electrochemical interface. For example, the distinction between non-specific adsorption versus specific adsorption. Ions in the outer Helmholtz plane that retain their solvation and are undergoing simply an electrostatic attraction to the electrode without changing their local solvent organization, versus ions in their inner Helmholtz planes that are either fully or partially desolvated and are now chemically bonded to the surface. And this is where the idea of pseudo capacitance and double layer capacitance comes in. And the view has been in the field really is that you really have either process A or process B, that these are two very distinct phenomena. On the other hand, what we're looking at here is, of course, a situation where you don't have a planar interface. And while what's happening at the outer surface might be explained by this kind of picture as I'm showing here, what's going on under confinement in layer materials, particularly ones that contain water and as bernocite does, we think is quite different. And it's actually more of a transition and shows the relationship between the kind of electric double layer adsorption processes at the outer surfaces versus a continuous desolvation of the cation. So at the end, you're left with something that looks like an intercalation reaction, basically determined by the solvation state of your cation and the interaction distance between your cation and your electrode. So that's a question that we have: is this a more appropriate discussion of electrochemical capacitance when you know that you have a confined electrolyte situation taking place? To look into this in more detail, we started to work with bernocite itself, that is bernocite that was synthesized directly. This is the structure of bernocite, so very similar to what I showed before, except now all the transition metals here is just manganese. You have a single layer of water, and with that you also have some cations present. We do an electrodeposition of the material, and these are these nanoflakes that are shown here, that we wanted a thin film morphology for the characterization tools that we were going to use. And this is the X-ray diffraction showing the layered structure. This material is of interest for high power energy storage, but also desalination, as well as catalysis applications. Interlayer spacing is about 0.7 nanometers, so fairly large, and it contains that structural water. Here's the electrochemical response. We see it has that very typical, potentially independent for the most part response. We do see some broad peaks that are present. When we try to deconvolute them from the background, which is really the predominant of the current, we find that they actually show very similar kinetic dependence, which suggests to us that they have similar kinetic limitations. They're probably due to the transport of similar species, which we think, at least from what we know so far, are potassium cations. Should also point out that the capacity that we're talking about here is very modest by standards of lithium-ion batteries. So we're talking about 0.1 electrons per manganese. And the question is this just induced charge, or is this actually a redox event that's taking place in the bernicite? We looked at the electrolyte dependence of this response from a couple of different standpoints. The first is to perform, in addition to what we did just before, the aqueous electrolyte experiments, we also did them in a bulky cation like tetrabutyl ammonium perchlorate and propylene carbonate. So no protons, no small intercalating cations present. And we find that the capacitance in that kind of a situation is orders of magnitude smaller than when we're in an aqueous electrolyte with a smaller cation like potassium. So since tetrabutyl ammonium is about 0.41 nanometers in size, it's unlikely to intercalate. So it really is telling us what's the outer surface contribution to the process. And so since we see this very significant distinction, we think that our electrochemical response is due to either cation insertion or potentially the role of protons. So to understand whether protons are contributing some of this capacitance, we, excuse me, we did cyclic voltammetry in both the potassium sulfate as well as potassium sulfate with a buffer, with 100 millimolar of buffer. So the pH here is maintained relatively constant or neutral. And what we see is that initially there is some capacity gain when we cycle in a buffered electrolyte, but then you see this very, very quick and sudden decrease in the capacitance. On the other hand, the potassium sulfate is very stable. Now, so we think potassium ions are what's driving the electrochemical response here. We see evidence of reversible structural changes from ex situ X-ray diffraction as a function of applied potential, as well as in situ Raman spectroscopy that are showing that the solid state structure is flexing or breathing, if you will. And that suggests that you have, an intercalation mechanism taking place, which many of us would consider evidence of charge transfer. And from the density functional theory simulations, these are done by D.N. Zhang's group at UC Riverside, we do indeed see that, when the potassium ions deinsert from the structure, that this interlayer spacing will expand. However, these changes are gradual and relatively small. So how do we think about this type of intercalation process? It looks similar to what would happen in a lithium-ion battery, except now you have some waters around and the extent of charge storage is a little bit smaller. Here's some more experimental evidence that just told us about how reversible the electrochemistry was. So this is electrochemical quartz crystal microbalance showing this almost linear change in mass as a function of applied potential with very little hysteresis. The change in mass was a little bit smaller than if we just expected potassium ions to be moving. So we think there is potassium ion insertion along with water deinsertion from the layers, like an exchange mechanism. And then we also applied an operando AFM technique where we measured the flexing, so the overall deformation of the electrode, and it also showed this really nice linear response. So what we think is happening here that's very special for bernicite is that water is essentially mediating the interaction distance. And to get this atomic scale picture, we really can't do it experimentally. This is coming from a reactive force field grand canonical Monte Carlo simulation by Audrey Van Duyn's group at Penn State. So I'm going to play this image for you. So the green is the manganese, the red is the oxygen. So these are the oxide layers. And here's the interlayer as potassium and water begin to populate the interlayer. And you can see that the potassium ions are staying relatively, they're pretty much in the middle of the interlayer. They have no particular affinity towards either surface. They're not really sticking to either surface, and the water is surrounding them or coordinating them. Some other details that these simulations reveal that I think is things that we haven't been able to verify experimentally but look really cool is that there's wrinkling of the sheets when there's some local inhomogeneity of the potassium insertion. So depending on exactly where the potassiums are, you see this kind of wrinkling occur to, I guess, accommodate the stress. We also find that the distance between the intercalating cation and the oxygen that's coordinating the manganese is essentially a descriptor of, the binding distance of the interaction strength. So going back to that picture we had before of electrochemical interfaces, the distance between the electrolyte cation and your electrode surface is important. So here we find that there's a very particular preferred distance of around 2.9 or so angstroms that the potassium cations want to be from the lattice oxygens. And it's a very significant energy penalty to move them any closer to each other. So why is this cation intercalation? Why does it appear capacitive? And here's kind of a big picture of many layers now with the water in between. We think that the presence of the water network here is very, very critical. The potassium ions that are intercalated end up having about half of their solvation now in the interlayer by these structural water molecules. The potassium has no specific site, that is, it wants to be distributed randomly in the interlayer. So that explains the potential dependence, as well as the fact that you have little structural change. So there's no first order phase transition. And the waters, again, we think play an important role in keeping the layers from rearranging when potassium leaves. So if you remember in our first study with the bulk sodium metal oxides, we found that once the water was present in between the layers, we no longer had that potential dependence of the cyclic voltammetry. So that kind of concludes our story on the very interesting aqueous electrochemistry of manganese oxides and the critical role of water in understanding their capacity of response. Where we're going with our work is to kind of take it up a step now that we know that these interlayers are essentially able to accommodate solvents and cations. We want to place in there more complex redox active species. The reason we want to do that, and is kind of going back to the first couple of studies that I shared with you at the beginning of my talk, where having access to this inner surface, if you will, not only will increase your surface area and the number of times that your reactant molecule will collide with the electrode and potentially undergo charge transfer, but we know from these theoretical studies that whatever's going on under confinement will have a changed physical properties compared to the bulk. So solvation is different under confinement. For example, viscosity is different under confinement. Hydrogen bonding of water is different under confinement. And we think that particularly for energetically challenging reactions, which is what we oftentimes want to do with electrochemical catalysis, this could be a very interesting knob to tune. And it's really a question now, I think, of going after the systems that can help you demonstrate what a lot of these computational studies seem to be showing. And the way we're doing it is through layered materials, of course, our favorite. We're looking at things like tungsten oxide hydrates, which we've used, which we also study a lot in our group. We're using some really interesting reactions to get organic molecules into the interlayer and prop open this interlayer to be about 2 nanometers. And we see very interesting electrochemical response. You would think with these greasy alkylamines, maybe your material would no longer be redox active in an acidic electrolyte, but we actually find that the electrochemistry is very, very reversible. And so the next step for this work is to start trapping redox active molecules within the interlayer and see whether they can undergo charge transfer that way. And there is work from folks like Graham Newton's group, where they looked at, polyoxymetallate clusters confined in carbon nanotubes that show that this can be possible, and there's some very interesting phenomena at work. Okay, so at this point, I'd just like to finish up the research part of my presentation. Thank again the wonderful work from my graduate students, my former and current graduate students, our collaborators, our sponsors, so the DOE, EFRC, for our work on Bernicite, and then the early career research program on our work on electrochemical reactivity under confinement, as well as our access to these user facilities. So before I move on to the career portion, I think this is a good place to stop and ask any questions that you may have. Should I go through in the chat, or does someone moderating?
Yeah, thank you, Prof. I had just quick questions. This is Janame Jaya. I had a few questions about pseudo capacitance. In slide 11, you compared the two plots and you were able to say that there was interpretation of capacitance in the second cycle. Could you just go over that if possible? Yes.
Mm-hmm.
So how are we saying that there's a presence of capacitance? I'm from power electronics background,
Right.
so I was just interested to know how you came to that interpretation.
Yeah, that's a good question. So we know that an ideal capacitive response in a cyclic voltammetry type experiment would essentially be a constant current as a function of potential.
Okay.
And so here, this is not an ideal capacitive response, but it is showing a more or less potential independent behavior over a broad potential regime, as opposed to the cyclic voltammogram on the left here, where you see these peaks that are indicative of a potential dependence.
Okay. So we are just we are having the plot one as a reference in this case.
Sort of, yeah, you can think of it that way. Mm-hmm.
Okay. And one more question, Prof, because I'm highly interested in the pseudo capacitance. Can this pseudo capacitance be used to increase the capacitance of ultra caps? Is that a possibility, or are there any limitations?
Yeah, that's really been one of the main reasons that pseudo capacitance has been studied, is been the idea that you would take these activated carbon materials. Ooh, let me go back. It's not where I thought it was. That you take these activated carbon materials and now you add to them like redox functionality. That's definitely, one of the things. Or you look at transition metal oxides, and that's where the Bernicite work came in, where people thought that, okay, since it's the transition metal oxide, now it's going to store charge through a redox process. What we're showing with our work is that it's actually not such a clear-cut distinction between these two, as you can tell just by looking at the pictures. When there's significant, when the intercalation processes involve structural water, they start to look kind of like the picture on the left here of a double layer under confinement. But it's a much longer topic, to understand exactly how to utilize pseudocapacitance for electrochemical capacitor applications, because there's a number of different strategies. So I already mentioned like tethering certain redox active molecules to carbons, nanostructuring transition metal oxides, or even looking at conductive polymers are all methods that are being tried for electrochemical capacitors. But I think that, there's a lot of, there's some overlap between the electrochemical capacitors and lithium-ion batteries, which is in the lithium-ion capacitor world.
Yes,
and so, yeah, there's a lot of ways that you could make devices like that.
And
Interesting.
sorry, just a follow-up. Does pseudo-capacitance vary with each cycle, or is it a fixed capacitance?
Ideally, it doesn't vary with cycle number, but in practice, because if you have a pseudocapacitance that does involve charge transfer, you are going to have the flexing of a material, the strain, you know, as atom bonds are being formed and broken. And that does lead to some limitation in lifetime. But typical numbers would be like for a double layer capacitor that's just purely double layer with a lot of the functional groups taken off, you should get about 1 million cycles. High energy density capacitor that includes some redox active functionalities, or a lithium ion capacitor, is about 600,000 cycles. And then, you know, lithium ion batteries are another order of magnitude down. So yeah.
And one last follow-up question, Prof. How would you distinguish between a contribution from double layer capacitance and contribution from pseudo capacitance at various potentials? How would we distinguish between the two?
So in some cases, it's very easy if the pseudocapacitive process is purely like a hydrogen adsorption event or something that's very clearly to distinguish from the cyclic voltammetry signature. In other cases, you don't really have an easy way of distinguishing them. And one of the points of this presentation is that maybe you don't need to distinguish about them because they contain features of both. That's kind of the story of bernesite.
Thank you very much, Prof. Thank you.
You're welcome. Thanks for coming to my talk.
Hi, Professor Augustine. That's a very nice talk. I have one question. So it's from the, so when you have a dopant, like you have, I think, used iron, cobalt, and those. So in some cases, I see like a more uniformity after like water exposure. What would be the cause for that?
So more uniformity. Is there a particular one in here that
looks? The iron one. I think the iron one, if I compare the pristine and the water exposed one.
Oh, this and this one?
Yeah.
Yeah. It's kind of hard to say because this is just one slice of a whole, you know, arrangement of particles. So we're looking at a very local thing. But what the main thing is that we see after water exposure that we either see an increase in the interlayer spacing or we see a significant variability in the interlayer spacing. And that we did not see in the copper containing materials. So there's kind of two possibilities. One is significant expansion, and the other is just a kind of a turbostratic effect, where these layers become highly kind of stacked and in a disordered fashion.
So for like lithium-ion battery, we see that manganese disproportion reaction, like the dissolution thing. So when you add this sort of iron and cobalt or copper, do you have those like reactions suppressed in these cases, like for sodium manganese oxide or like?
So you mean that there's disproportionation reactions?
Yeah, like the manganese, I'm talking about the lithium case.
Oh, okay. Yeah, so the manganese becomes soluble. You know, I'm not sure what the latest understanding is in the non-aqueous sodium ion community on that. That's a good question, though. I really don't know. I have to say I'm not quite sure what those studies are showing. Yeah, that's a good question, though.
I think we have one more question in the chat. So it's about the trapping you mentioned. So do the molecules would be added during the synthesis of the material, or sort kind of activation exfoliation after the material is synthesized?
Yeah, good question. So we are planning to do it right now. Our route is during the synthesis as opposed to after the fact. So, well, actually, I should say no. We're doing both. We're doing both approaches. That's the truth. We're trying both. Yeah, and different hosts.
I have a question if we have some time. So it's kind of a two-part question. So the first part is, it sounds like you think of these processes as like kind of a continuum between like the lattice parameter that you start seeing the, yeah, exactly this slide. So the second part of that question is, do you think that the critical like spacing between layers is a function of the interaction strength of your particular ion, for example, and like the surface of whatever material you're working with?
Yeah, first I have to ask, are you in the Mantherm lab?
No, I'm actually in the Mullins lab, but good.
Okay. It looks so familiar to me, that lab that you're in right now. It looks like one of our synthesis labs when I was at
I usually have a background because it is kind of chaotic, but
yeah, so your question was about the identity of the cation.
or just like, do you think, well, first of all, do you think there's some critical D spacing where you start having more effects from confinement? And then do you think that critical spacing is a function of the interaction between the ion and the surface?
So yeah, I don't think I can be quantitative in your answer, but I would say that in my opinion, it's going to occur as soon as these cations have to undergo any sort of solvation, whether it's partial or complete. Then you start to see the role of confinement. And yeah, there's been some interesting, again, computational works about the concept of like frustrated solvation, that the water molecules that remain are now, you know, undergoing more charge transfer or more electron sharing with the cation than they would like to normally. But yeah, I think that it will basically be as soon as you start to affect the cation solvation of the first, let's say the first hydration shell, you're going to start to see those effects.
Yeah, and so that's mainly a physical thing and not like adsorption energy.
Yeah, but I think the two are related. There's a really great, at least the way I like to think about it is taking some understanding from the planar interface side. And there's a really nice review paper on cation effects in the double layer that I'm happy to share with you. It was co-authored by Matthias Wagel at Boston College, and I find it to be very nice. And it actually presents this desolvation as a chemical reaction, you know, with the free energy change and all that. So I think it makes sense to me to think of it that way, and then to quantify, you know, the despacing based on when you start to see that. The other way to do this, and this is, I think, what is done more often computationally, is when you start to see that the double layers that are, you know, at these surfaces, if they are initially isolated, if you start to bring them closer together, when the double layers begin to overlap, that's another way I think of saying this is where confinement effects begin to dominate. I know that there's groups, including ours, that are working on synthesizing a series of materials with different interlayer spacings, like Patrice Simon has done that with graphene oxides. But it is challenging because it turns out when whatever stuff we put in the interlayer, it ends up having its own interfacial properties. It also ends up, you know, you have to control the concentration of those pillaring molecules so that you don't block off the intercalation process. So you have it pillared just so. So we haven't, I don't think, been able to really show this experimentally in the case of 2D materials yet.
Yeah, so I asked that question because the materials I work on is nitrogen-doped carbons, and it seems like you can tune the d-spacing by changing the nitrogen content, and that also changes the interaction energy. And so I'm wondering if like there's some combined parameter of like interaction energy, critical spacing, or something like that.
Yeah, I would imagine that to be the case. That's very cool.
Thanks for your answer.
Yeah. Okay, any other research questions?
Prof, I just had one more question related to pseudo capacitance. So how would we simulate this? Is this all experimental, or is there any way to simulate pseudo capacitance or find out variations of pseudo capacitance with materials?
Yeah, so all of our research work is experimental. We do have computational support from other research groups for things like density functional theory. It depends on what you're trying to simulate. Like, again, if it's a planar type of interface process, it's relatively straightforward, and one can simulate, you know, a redox active molecule tethered to a surface gives a characteristic surface adsorption wave. I think the best place to start is in the textbook that Brian Conway wrote on electrochemical supercapacitors, because it really kind of shows how the theory of pseudocapacitance is built up. It's very useful.
Thank
Highly
you. Thank you very
recommend
much, Prof.
it.
Thank you.
All right, so in the last few minutes, I was going to share a little bit about my career path and some interesting stories, perhaps, that you may find useful for your academic and research journeys. So first, I was born in Poland. And so Marie Curie is an important hero for me, not just as a female scientist, but because she was also born in Poland. And one of my first interests, and this is a book that is in Polish that I got when I was a kid, was actually in rocks and minerals. And I just remember being fascinated by the shapes of minerals and rocks. I did not become a crystallographer, but I do recall this being just fascinating for me as a child, and having a rock collection and growing crystals and so forth. Then in the early 90s, I moved to Chicago. And I say early 90s because this was the era of the Chicago Bulls. So we were all into it, but we moved to Chicago. It was a major experience for me. The first time I ever was on a plane was basically to move across continents. And then for my bachelor's degree, I attended the University of Arizona, which is an interesting story. Has some, teenage rebellion involved, where I said, I don't want to go to University of Illinois, because that's where everyone from my high school is going. And the cost at that time was similar to attending Arizona out of state. So I made it out, went into the desert, and attended U of Arizona in beautiful Tucson. All's well that ends well, because that opportunity brought me to a very caring, very collegial department where I had numerous research opportunities. And I also got to attend a seminar by Bruce Dunn, who would become my PhD advisor. So I attended UCLA for my PhD, and then I attended UT Austin for my postdoc. So I was asking, I think it was Jason, where he was sitting, because his lab looked so much like my lab when I was a postdoc in the Mantherum group at UT Austin, and then finally ended up making my way back east to North Carolina to become a faculty member at NC State, where I've been since 2015. So one other thing that I will share with you as I kind of go through my journey is, this is the picture of the world. This is the world at night. And I had a very unique opportunity when I was a grad student at UCLA to attend a workshop in Ethiopia, so right around here in Addis Ababa, where we met to talk about energy and materials for energy. And it really opened my eyes to the global inequalities in energy, as well as engineering education. So Africa is a continent of more than 1/6 of the world's people. Tremendous population, but only about a quarter of them have access to electricity, as you can obviously tell from this picture. The electricity that is available is fairly unreliable. Now, for me as an academic professor, the other thing that's really important is these last two bullet points, showing the very challenging research landscape on the continent. The African scientists and engineers were accounting for less than 2% of scientific publications, very similar in patents granted. And there's really a very small density of scientists and engineers per 10,000 people. And so it's a challenging environment for many reasons, but we know that there's some important things going on. So one is that we know that places like sub-Saharan Africa is where most of the growth in energy consumption will be coming in the next few decades. So places like the US, we will have relatively constant energy use projections due to our population growth and the fact that we already have an electric grid. But these economies that are rapidly developing have a need to be electrified. At the same time, it's been recognized that there's a big mismatch between the places that have been responsible for most of the greenhouse gas emissions and the places that will be taking on the burden of climate change, that will be most affected, if you will, by climate change, because one is economics, the fact that their structures are maybe not built to withstand the tremendous force of hurricanes these days. So there's this really important study that came out a few years ago showing that. Now, what's the opportunity? There's an opportunity for us to recognize that these countries could become electrified using renewable power. And indeed, when you look at the current and the projected use of non-hydropower renewables, these places that are rapidly growing their electric grids will actually have more net electricity generation from renewable sources than others. So this is kind of a big intro for a project that is right now in modest in scale, in a collaboration between myself and my partner in Uganda, John Paul Aneku, who's a lecturer in physics at Makerere University. And him and I met at this workshop in Ethiopia when we were graduate students. And here's us a few years back, I think this is in 2013, pitching our project at the African Materials Society meeting, African Materials Research Society meeting that was held at the African Union. So that's the symbol of the African Union. And it's become a project that's very near and dear to my heart. It's a project that involves experiment kit development and shipment to our partner universities, primarily in Uganda, where we try to support them in engineering and science by giving them opportunities for hands-on research. And we find that these experiment kits that we send, they're used not only in classrooms, but they're also shared with local communities. So this was an example of dye-sensitized solar cells in John Paul's classroom at Makerere, and then his students just a few weeks later doing the same experiment for an open house at their university. So if you're interested in the project, we're happy to chat more. This is our contact information. These are some of the students in the past that were involved at NC State. Okay, very last thing, STEM career, what I've learned so far. I think that one important thing to just keep in mind is that if you're interested and passionate about something, you can learn it and you can become excellent at it. I think this is really key, is find what you're interested in, find what kind of strikes your curiosity and kind of go with it. The second is that networking is important. The people that you meet throughout your research career, including in undergraduate research or graduate research, you can oftentimes stay in touch with them throughout your careers, and it's fascinating to see where people end up and just to continue learning from each other. So I think this is really important, and also a reminder how important it is to be collegial at all times. The third is to look for the right role models. Look for people that inspire you, that their career, their research program, their ability to have a particular work-life balance. Look for people that do what you would like to do, because there's a lot of different ways to do research or academia. Find someone that you can see as a role model and kind of use that to help you, particularly when things get very stressful. And that includes, listening to advice that people give you, including criticisms, and knowing what to take to heart. So as a woman in science, I've gotten a lot of different advice throughout my career, but some of it, even when it was coming from very distinguished people, I knew that I could not actually take that and use that in my life. And so that leads me to the next point of taking the road less traveled. I think that's really important. Follow your path. Don't follow what other people do, particularly if you're an underrepresented minority or a female in science and engineering. You should recognize that the path of people that have come before you is probably not going to work for you, just because you are unique. And your needs will be unique. So follow your path in life and in science, and that will give you the most happiness. And importantly, we need creative individuals with diverse perspectives in science. Like I showed for the SciBridge project right now, you can look at the map of the world and see that we are missing tremendous perspectives in science and engineering, and so that needs to change. And so just to close out, since I know I'm a little bit over time, these are a couple of pictures that at least for me, you know, when I look at them, I have to kind of pinch myself with things, because my career hasn't been easy, and I wasn't, you know, in the most preeminent academic institutions. I didn't have, you know, all the scholarships to go to college, and my parents were working class. I had no idea what undergrad research was and all this other stuff. But here's me when I got the Sloan Research Fellowship with my daughter and our university chancellor. So this is my life. This is what, you know, science means to me. It's going to be different for you, but you can do it. And then a couple years ago, I was invited to talk at a panel that included Tito Abrunia, Esther Takeuchi, and Stan Whittingham. And I had to kind of pinch myself that they asked me to come talk about electrochemical capacitance in that case. And so just, you know, follow your path and follow your creativity. I think we really, really need that in science and engineering. So that's my perspective so far. I hope it's useful for somebody. And I'm happy to always chat more if there's any questions.
Thank you, Veronica. This is just absolutely wonderful to hear this perspective, and also your very fundamental science that you do.
Thank you.
So thank you so much. So any questions from the students? I prefer to remain silent most of the time, but so please go ahead. I think maybe Professor Augustine can spend a couple of more minutes, I guess. So
sure, yeah, I'm happy to take, you know, questions, or if you want to hear my perspective or elaborate on anything, let me know.
If not, then I actually really liked the SciBridge project. I think when I met you for the first time at Scilog, you know, and then before that I only saw that. So it's really exciting, that SciBridge concept and the whole network that you have built, and you were so passionate about it. So just a shout out to that, and that's amazing.
Yeah, now the project is entirely being handled by it's a student organization at NC State, and they've done really amazing work. In addition to, you know, the resources that we send to our partner universities, we actually sponsor senior design teams here at NC State, like one senior design team a year, where they come up with experiments for our program. So it's an engineering challenge with you know, the constraints and everything that you need to come up with an experiment that will work for our workshops. So
that's just amazing. Very good. So did you have a chance to visit your partner university in Uganda before the pandemic?
No, the time that I had the opportunity, I couldn't go because my daughter was like 2 months old. I thought I would go before she was born, and then I realized afterwards I can't go. I was still nursing, and it would have been just a nightmare. But he did come to visit me at NC State in 2016, so it was really nice. He was here for 2 weeks. He was in my lab and like visited a lot of labs at NC State, met a lot of different people. So that was really cool. Yeah.
That's wonderful. Very good.
Thank you.
And yes, this picture should be very memorable. I have one from Scilog with Stan, and just in the evening, having probably wine and around the fire.
Yeah, you know, that's the other great thing about electrochemical sciences. I think overall, it's a very, very supportive community, you know, overall.
Very true.
Every field will have its, you know, special